Here is a new concept for us. It's a new force. It's called the Centripetal Force. We are familiar with it if you've ever been on a merry-go-round, or you have been on an airplane that's doing a pull-up, or you've been fortunate enough to fly with someone who will do a downward loop. Then you have experienced 0 G's. You've experienced going light at the top. You can experience this in a car. If you're at the bottom of a hill going up, you'll feel centripetal force. You'll also feel it when you go around a curve. And that's because velocity is a vector, so we don't have to change the velocity. These two velocities are the same. We're traveling in a circle at constant velocity, but because the direction of the vector is changing, not its magnitude, but a vector has two components, its magnitude, its length, and its direction. Because the direction is changing, there is acceleration. And that acceleration, caused by the fact that when you're in a car and you go around a circle, your body doesn't know that the car is going around a circle until the seat belt and the door act on you to change your direction. That's Newton's first law. You will continue in a straight line until the force, the seatbelt and the door, act upon you to change your direction. So you feel as if you're being thrown into the door. But in reality, it is a center-seeking force that is responsible for this. Here's the velocity changing. So that's delta V, and it's pointed toward the center. And here is another triangle. So we have this triangle. I picked this vector up and moved it here to make this triangle. And here is this triangle. And so because the triangles are similar, remember we can write that corresponding parts of similar triangles are in the same ratio. Delta V, the short leg, over V is the same as V over R in the bigger triangle. And I can multiply both sides by V, and I get delta V, which for all intents and purposes is acceleration, the change in velocity with time, is the centripetal acceleration. Centripetal is Greek for seeking the center, or center seeking, V squared over R. So if you whirl, we're looking down on a horizontal circle, we're holding a string to a ball, and we're whirling it around at constant velocity, and we will find that the tension that we must provide to keep the mass in orbit, because if we let it go, it'll just fly off, is mv squared over r. If I'm whirling a mass around and I let it go when it's facing you, it will not hit you. There's no such thing as centrifugal force. There's no force outward toward you. If I let it go, when it gets around to here, it's going in that direction, it'll continue to go in that direction. If I want to hit you, I have to let it go when it's here, because it'll fly toward you. It's traveling now, it's traveling toward you. Here it's traveling that way, here it's traveling that way, and here it's traveling toward me if I let it go. So depending upon where I let it go, there is an inward-seeking force no matter what happens, and the centripetal force is mv squared over r. There's a ton of stuff we can do with this. Airplanes and gravity depend upon centripetal force. So this is a very important equation, that the centripetal force, the center-seeking force, if something is in a circular path, is mv squared over r, where this is the radius of the circle in which the object is moving, m is the mass of the object, and v is the velocity. So the centripetal force, the inward-seeking force, is mv squared over r. Something has to provide the centripetal force. When I whirl a mass around my head, I'm providing the force by pulling on it to keep it in orbit. When a satellite is orbiting the Earth, the gravitational field will keep it in orbit. When a car is traveling in a loop, it is the normal force that will provide the inward center-seeking force. And if I have a round spinning lazy Susan or table and something sitting on it, it's the force of friction holding that object in place that provides the center-seeking force. So we'll always be asking what force provides mv squared over r. It doesn't just happen. We have to have gravity, friction, a tension on a cable. Something has to provide the centripetal force. And we'll get into that as we continue and do a couple of examples coming up.